Well, welcome to Training Tuesday, and thanks for joining our webinar today. I'm hanging out here with Mr. Chuck Hoke. I am Heidi Reese, Training Programs Manager at Dayton Superior, and we have an exciting Training Tuesday ready for all of you. But first, just a couple of housekeeping items to go over before we get started. So like normal, I wanted to remind everyone that you are muted so that the presentation can be conducted without any outside disturbances. Just please feel free to go ahead and ask any questions or comments through the Zoom functionality, chuckanality, the Zoom functionality. There is a chat and or a Q&A. Both of those are turned on for you guys. Feel free to use them throughout and I can talk back with you. We'll definitely have a question and answer session at the very end for you. As a reminder, all of these webinars are recorded and placed on Dayton Superior's YouTube channel, as well as DaytonSuperior.com's website. Just search Training Tuesday and you can find the latest and greatest. Okay, so one more little topic. This presentation is intended for training purposes only. So anything that we talk about within this webinar concerning products, please go to DaytonSuperior.com or hkcomposites.com. I think it's hkties.com. And you can find all of the technical data sheets and the safety data sheets, all of the information on how to utilize the product. So you may know Dayton Superior for the accessory lines, such as the precast that we're going to be talking about today. But did you know that we also are the leading provider of engineered solutions and products in the concrete construction industry? And if you didn't, here's a little bit of blurb. We do specialize in those accessories I talked about, chemicals and forming, and we have proven results through our Simon's forming and shoring portfolio. The systems are very adaptable, they're obviously strong, and they save labor costs, and a lot of them connect with each other, so it's very efficient. In addition, we have for the accessories, the bridge deck, rebar splicing, precast items, tilt-up construction, as well as engineering solutions, products and trainings that are geared for what you need. So the whole single source value add concept there. And one of the accessories that we definitely have is within the HK Composites, and they achieve that maximum thermal performance within the building using their most unique system, combining insulated panels with tie connectors. And here to talk with us on HK, as you are perusing all of the different solutions with accessories and forming there, is none other than John Osweiler. He is with the sales there for HK Composites. He's a lifelong Iowan? How do you say that? He's from Iowa.
Just don't ask Minnesotans what we're called. We're okay.
Wow, I'm good, aren't I? Go Iowa. So, of course, for that college, he attended Iowa State University to get his degree. He has been in the construction industry for 30 plus years, mainly working within the insulated concrete wall arena and the insulating concrete forms and sandwich panels. He is a green building certified as well as LEED, LEED, AP, BD plus C. And for those of you who know that, kudos. He is credentialed for LEED and green, basically. In addition, he is an ACI tilt-up technician, and he is here to talk to us about all things HK for precast applications. So take it away, John.
Thanks, Heidi. Thanks everybody for being here. We're talking today about something we've talked a little bit about before, which is basically sandwich panels and how these ties relate to that. And specifically today, we're talking a little bit more on the precast side of things, whereas I think next month we'll focus a little more on site cast tilt. But in precast, it's a pretty unique application, and there's a system that we use almost exclusively in precast that we're really kind of I think I just talked and muted this whole time. Can you hear me,
So
Heidi?
you just, the very end was muted. The rest of it, we heard you. So you're
Oh,
good.
okay, good enough. Now I got to figure out how to go.
And you're muted again.
Okay, I'm not going to do that anymore. Heidi, I cannot get to the next slides for some reason.
All right.
There we go. I might have to ask you to do that. So in an insulated sandwich panel is really quite simple. We've got two concrete layers, or we call them Ys, with insulation in the middle, and that's connected with in our case, non-conductive connectors. We call them wide connectors, and there's a couple different ways to do that. There's different thicknesses of insulation, and there's different thicknesses of concrete, and ways to do that on either side. We're going to focus on one in particular, but we can go to the next slide. But before we do that, again, this is about the simplest wall system you can provide a customer, or you can make for yourself. This is two layers of concrete with insulation. In every, now there are things holding that together. There's connectors. There happens to be rebar in there. There's reinforcement. There's other things to help us get these panels in place. Inserts for braces, inserts for lifting these panels, things like that. But the core of it is insulation and concrete, and that's all you need. This is really important in every part of the country, whether it's southern Florida, Oregon, or even Alaska. Frankly, for standard ambient type facilities, this is all we need. We don't need a coating to make it work. Usually there is one. We don't need additional vapor barriers or rain screens or anything else. This as a final assembly is incredibly efficient. Next screen.
And you should be able to do it now. Give it a try. If not, I'll still do it for you.
For some reason, it's just not doing it.
Okay, I'll take it back for you.
It worked when we practiced, didn't it, Heidi?
I know, that's how it always is. All right, there we go. Teamwork.
Thank you. So these different wall types that I mentioned are they're similar, but actually when we get down to it, they're pretty different. We've got walls that are non-composite in nature, and that's where we take a standard structural tilt wall, and then we add insulation and a face off the side of it using a certain connector type. And those are out there just doing their specific job, meaning the insulation is insulating, the face is out there looking pretty, if that's what we want it to do. It's protecting the insulation, but it's not structural. On the right side here, you're looking at what we call a composite wall panel, where the two Ys, the two layers act together. And the way that they're acting together is through a special connector that helps it share that load. Next screen. And those Ys or layers are usually, not always, but they're usually equal in thickness. So a typical composite panel may be 3 or 4 inches of concrete on each side with, let's say, 2, 3, 4 inches of insulation in the middle. Now, this is saving a lot of concrete from a traditional panel that might use 2, 3, or more inches of concrete to, in effect, do the same thing. This is really important to precasters because it saves weight of the panel. It allows for taller panels for the same weight when we're transporting in the panel. That's important because we're going down the road and we have limits on what can be done there. And that composite action is very effective if we use the right connector to do it. Next slide. In addition to the connector, which is thermally non-conductive, it's not a metal connector we're trying to isolate the two layers of concrete from each other from a thermal standpoint, just not from a structural standpoint. So we're sharing the load, but we're keeping everything thermally broken. And part of doing that is also keeping the rest of the panel thermally broken by doing monolithic insulation. So we want that mass of that concrete to work to our advantage. And the way we do that is to go edge to edge, opening to opening with the insulation. So what you're seeing here, and it's to the uninitiated who haven't seen this before, it's very concerning. The only thing holding that panel together are these connectors. However, they're highly tested and they can do the job we want them to do. But that is what holds those two wides of concrete together without bridging thermal energy across them. Next slide. Here's an example in a precast plant of how the system goes down. So we pour the face concrete, or rather, we're in the bed at the precast plant. The foam comes with slots already in it, and it comes cut for that panel. We put the face down, or one wide of concrete down, lay the insulation, and insert the connectors. And then these are obviously done in the freshly placed concrete, so it's still plastic. We get good consolidation, get all the connectors in place. Whether these are pre-stressed panels or not, this process is the same. Once that's down, then we can put in the other wide of concrete, put in the steel or bar, inserts for lifting, and there we go. We're ready to take this to the site. Very simple. This is very similar on the other non-composite style of panel, except we just take some extra engineering when we're doing a composite panel. These things get moved a lot more than site cast tilt-up panels do. So we've got to take that into account as well. And next slide. There are different ties that are used in the precast industry. Traditionally, there have been a lot of steel ties that have been used, M ties, some different things like that. There are low conductive ties. And then there are some that are made of different materials that may or may not have a certain amount of conductivity. There's a lot of stainless steel ties that are being used. On the bottom are kind of indications of some truss systems that are also used in precast to get composite action out of the walls. These may be steel trusses, it may be stainless steel, fiberglass, basalt, expanded metal, different kinds of things. They're pretty effective in gaining a certain amount of composite action, but as this industry has developed, there's different ways and different methodologies to determine composite action. And what we've determined is that we need to be a little more than generic about it. Also, when we go with truss systems, there's usually issues with some gaps between the foam when we try to get those put in there. And they don't allow for a lot of special conditions. So they work pretty well to get the action we want, but certainly if they're steel, they don't do what we want to do from a thermal standpoint. Next slide. And here's an indication of what that means. So if we've got a certain cross section of steel, and this is something that was calculated some time ago with a certain amount of steel M ties in the panel and what the total cross section would be, and they were industry standard numbers. So when we look at just how much steel ties used across a panel reduces the R value or the efficiency of a panel, we can see that that's getting close to 30%. If we have a certain amount of solid concrete in those panels, we could lose half of the efficiency of the panel just through thermal conductivity across those two faces. When we use a fiberglass or plastic connector that's able to deal with it, we don't lose anything because we don't have that thermal drive across the panel. Next slide. The other issue when we're using other kinds connection devices in a panel is that sometimes they don't give you enough strength, or they don't transfer enough shear or whatever loads across that panel to avoid solid sections. And that's what we want to avoid. For instance, in this picture, we've got solid zones around an opening. That's a no. We're probably going to have some cracks happen there, and or some condensate form due to thermal bridging. Um, Oftentimes with other systems, you're also getting composite action from solid zones that are kind of baked into the cake in the panels at lifting inserts, at bracing inserts, maybe at the parapet areas or at the base of the panels. We want to be as true as we can to monolithic insulation. Next slide. The detailing of the panels matters quite a bit. You'll see in this particular case, we've got an outside corner, and traditionally um, a turn back of the insulation isn't done. Well, we need to make sure we do that, because if we have, like in this case, a thin brick on the panels and we don't turn back the insulation, then we're going to have some cracking and spalling occur. And that's a pretty big problem when we have an architectural finish like this on the panel. That's going to be difficult to fix. It's very easy to detail these correctly, and we provide those specific details, whether it's for composite or non-composite panels, to make sure that we can give the customer what they need for some long-term performance. Next slide. All of this together, when we use non-conductive ties, when we extend the insulation all the way to the edge of the panels and all the way to the edges of the openings, that lets us use the mass wall effect, which is actually using that massive concrete on the inside of the facility to our advantage. So it's going to be able to take on energy, actually absorb BTUs, and distribute that over a greater period of time, so that we have less swings during the day or during the week, when we have different loads actually come into that area. So the thermal mass is something that actually is very effective, and it's actually used by ICC in the code requirements for insulation thicknesses as well, which we'll see. Next slide. We're going to see that again. The important thing here is that the insulation is continuous, and that when we're looking at the codes, they really do mean continuous insulation. So we need to have, all the structural parts of the panels need to eliminate thermal bridges, basically, and we need to have that insulation go and meet each other. Meaning, we really should have the wall insulation meet the roof insulation, meet the floor insulation. Somewhere in that wall, it's got to be continuous, if we don't have the bridging that can occur in other methods of construction. Next slide. That gives us the benefit of using the ICC requirements to show how beneficial mass can be to us. So in this case, just the highlighted red boxed areas, if you're in zone 2 or 3 in the country, you're going to see, let's pick a metal building. ICC requires, these are minimum requirements, of course. They're going to require that you have an R13 in the walls plus an R6.5 continuous insulation on those walls. Again, they require continuous regardless. But if it's a mass wall, meaning if it's a precast wall with the mass that's working to our advantage, you only have to have an R5.7 and you're done. So instead of having a total of 13 plus 6.5, 5.7 in the mass wall, you've met the requirements because it's that efficient. And you can go to the right and look in different zones. Let's go to my zone, for instance, in Iowa. I'd have to have on a metal building R14 of continuous plus an R13 in the walls. But if I have a mass wall, 11.4 continuous. That's it. That's 2 inches of insulation. Back in the original case in zone 2 with that R5.7, that's easily done with 1 inch of insulation if you have a mass wall. Now, we see that designers are asking for more than that at times, but If we're getting into the value engineering part of things and we still want to perform this wall, we can do some pretty amazing things when we have mass working to our advantage. Next slide. The other thing that we gain by controlling the thermal bridging within a panel or across a panel is controlling condensate or controlling moisture that forms. Um, the lower picture is an indication, is a thermal view of a dormitory in Texas that was freshly built, and these are spandrel panels. They had solid zones at the base of the panels, where you can see the red. You can see this is taken in the winter. You can see the heat from the base of the panels. Well, that translated into condensate formation at where these panels inside met the floors, and then that turned into mold. Well, that's a problem. That is eliminated when you eliminate the thermal bridging and have continuous insulation. So it's not just an energy issue. It's not just a energy savings issue. It's really a health issue as well. When we have thermal bridging, and different parts of the country show this in different ways, but we can almost assure ourselves that we're going to have some kind of condensate form at some time in the year, and that's a problem that's difficult to solve. So this is really why we want to be as pure as we can to the monolithic edge insulation. Next slide. We can do a dew point analysis for you. Vapor drive is an insidious thing, and it's going to happen if we have a dew point. It's going to cause condensation if the dew point is in the wrong place. So every project we do, we're going to give you a dew point analysis to show you that this wall is going to perform correctly and avoid creating a dew point within the wall somewhere where it's going to cause a problem. Next slide. I guess we already talked about energy codes, but again, these mass walls that are done correctly allow us to take advantage of a lot of the standards and codes that give it certain credence. We will help you in meeting those codes, help you with the studies that are needed, the different analyses that are needed to show that it's met, as well as helping determine maybe what type of insulation. There's different types of insulation you can use in these walls. It might be extruded polystyrene, it might be expanded, different types of ISO type foams. We'll help you with that to get to the R values and get to the performance we need as easily and as economically as possible. Next slide. So we are highly tested and have everything we need to comply with anything an engineer or a precaster might need. Composite walls require a little extra engineering, a little different engineering than the standard walls do. So we have software. Dayton has Composite Works coming out, which will also help engineer these panels for composite action. But we take the values of our connection devices. We can plug those into these. Next slide. And take into account all the loads that are going to be on these panels, and then show what the stresses are going to be on them, for example. So lifting and erection, the stresses in place, wind load uplift, that kind of thing. Seismic, if we have it. We also, for precast, have to keep in mind the transportation loads stresses that are going to be on these panels. So we do look at all that, and then we help determine, next slide, things like what the spacing of the connectors is going to be, where we might need extra connectors, where we might be able to space them out more. There are sometimes some pretty complicated panels that have column loads in them, and they're getting lifted weird, or they're getting just some really high wind loads, whatever it might be. We take all that into account, and we adjust the spacing and position of these connectors to deal with all that. Next slide. We put all this out in a booklet for you, shop drawings with the installation. In most cases for precasters, we're either sending you the installation that has slots already in it, or we're sending the installation fully fabricated, as in this example, where every sheet is cut. It comes to you in a bundle. There's no waste on site. You just take it out, you open up that bundle when you're ready to cast that panel, and each sheet is numbered and ready to lay down with all the special locations for connectors and inserts of different kinds are already accounted for in that. We're going to have the thermal analyses done for these things. Different engineers have gone through them uh, to make sure everything is valid before you cast. So next slide. So then, like I said, we can get it to you really three different ways. One, we can go with composite ties only. That's a little difficult, a little more difficult than a standard tie, which is a solid round pin. In that these need a slot, and the slots can be done in different ways, but it's not all that handy. So for precasters, I would say a good percentage of what we do is partial fabrication, meaning we'll send you insulation with slots already put in place at a standard spacing. That's pretty typical. And once anything kind of differs from that, you might have to add a few slots here and there on your own, cut your own insulation for the panel, but that's a very economical way to do it. Or there's what we call the full fabrication, where we send the insulation fully fabricated for each panel. There may be different spacing, there may be all kinds of different locations of connectors, but we also take into account if we have to, let's say, thin up the insulation in certain areas to get a lifting insert installed in that position. Maybe the insulation has to go from 3 inches to 1 inch in that area to get full embedment of an insert. We take care of that in that particular case. So anything at any level you need, we can help you with, and any level of engineering support, both HK and Dayton Superior can help you with through all facets of the panel. So don't hesitate to call us and ask those questions and ask for more. So if anybody has any questions at this point, we'd love to field them.
Yeah. Thank you, John. That was great. I feel like I'm the expert slide turner now. Yeah, like John said, if there's anything that you have as far as questions, please feel free to go ahead and put that in chat or the QA section.
I was trying
Okay.
every button that they would work.
We've got one question that says, is there a simple way to calculate the degree of composite action with the HK connectors so our engineers could do the design using the HK connectors? Or must it be the design with the HK team? So does the HK team have to design it, or can they?
So no, we can give you the values for the connectors, and you can input that into whatever system you want. I'm not an engineer, but I am aware of some of the changes that have happened, and the percentage composite action theory of things is sort of giving way to the beam spring method of calculation, which is a little bit different. So if you're interested in the system, we're more than happy to do those calculations for you to help you design those panels. The biggest thing that we're asked generally is, can we space these things out a little bit more? And I would say in general that yes, we can. Standard spacing is 16 inches on center, and that's going to take care of really the bulk of what you could possibly run into. But for economical reasons, and economical might just mean labor, maybe we can get it to 24 inches on center, or 24 by 16, or whatever. So if you contact us directly, we can help you with those calculations, or we can provide you with the connector strength data where you can do that yourself if that's the methodology you want to go with. That's fine.
Great. Thanks, John. Anybody else have any questions? Just to remind you that we put these out on DaytonSuperior.com. I don't send emails out anymore to let you know where they are, but about 4 o'clock you can find the latest and greatest. Just search Training Tuesday on DaytonSuperior.com, and it'll get you to a page that has the 4 latest one we've done. Plus, I think this is, what, Chuck, the 110th webinar that we have held for Training Tuesday. So kudos, John. You know, put a hat on and a little squeaker.
If I was the 100th, maybe I should be more excited, but 110.
Oh, come on, 110's cooler.
All right, okay.
Well, it doesn't look like we have any more questions. If you find that you do, please feel free to reach out to superiortilt@datesuperior.com. We'll get it to the right people. And everyone, have a great Tuesday. And I appreciate you coming out and listening to our Training Tuesday. Again, thank you, John. Great information.
Thanks,
Thank you, John.
Bye now.
Bye.